The next of our tests for convergence is the direct comparison test. The direct comparison test allows you to take the known behavior of one series and use it as a tool to determine the behavior of an unknown series. There's a series whose behavior you don't know but want to learn. There's another series whose behavior you do know. You can use it as a tool or as a mechanism to find out how this other series behaves. So the requirements are this. Direct comparison test says this, that if, so suppose we're given AN and BN, two series. Suppose we have two series. And suppose we know that if 0 is less than or equal to AN is less than or equal to BN, I don't think we want equal to. These are positive valued. And AN is always smaller than BN. Each term here, if you expand this out, the first term is less than the first term here. The fifth term is less than the fifth term here. The 10th term is less than the 10th term here. So these values are always less. This has, and in fact, it's a variation on the theme of the squeezing theorem. You can probably see the squeezing theorem happening here, and that's really sort of what happens here. It says this. Suppose we have that condition met, so A is always less than B, all right? Then we may say this. We may say the following. So the idea is this. Here's 0. It's a hard floor. Here's A working out here somewhere, and here's B working out here somewhere, right? We know we have a hard floor down here at 0, right? The first piece is this. If the larger one, if B is finite, if this adds up to a finite value, then the quantity of A must also add up to a finite value. The question is, can this go off to infinity? Can this go off to infinity? No, it cannot go off to infinity. Now, we know it doesn't oscillate because we have this restriction. So we know neither one of these is oscillating positive, negative. So that's right out. So the only way that A might diverge is if it goes off to infinity. So really what we're going to say is this. Suppose you know that B, that sum is finite. The question is it possible for A to go off to infinity? Well, it's not, because A is trapped beneath a finite value for B. That means A must also approach a finite value. All right? So it says this. If Bn, let's say it this way. If this sum if the larger one converges, if the larger one is finite, the smaller one must be finite. It cannot escape to infinity. It's this squeezing theorem effect that's happening here. Then converges. So, suppose you know that the large series is well behaved. This is corralled between 0 and the well behaved. It must also be well behaved. It cannot escape off to infinity. All right? On the other hand, it says this. If suppose AN is a series whose behavior you know, suppose AN diverges. What does that mean? Okay, here's 0, the hard floor. Here's A working here somewhere, and B is always above it. Now what we say is this. Suppose this one actually does push its way off to infinity, out of the picture. The question is it possible for B to remain finite under those conditions? Well, remember, B is always bigger than A. B is bigger than A, and A is going off to infinity. Therefore, B must be also pushed off to infinity with it. So if AN diverges, then so does BN. Actually, this is just a contrapositive of this statement, if you know what that means. But if you don't, that's fine. And so that's the direct comparison test. If you're directly comparing the behavior of two series. It turns out, now this is not brutally challenging to prove, and it involves sort of the flavor of a squeezing theorem argument. So we will simply accept the direct comparison test as accurate. But the direct comparison test, as a practical matter, doesn't get used very much. Anything you could use the direct comparison test for, you could also use the next tool, which is called the limit comparison test. And the limit comparison test is much easier. You're using a more powerful tool to do the same job. So that's really all I'm going to talk about, the direct comparison test. In a direct way. But now we're going to talk about the limit comparison test. Again, the limit comparison test says assume we have these two series given. My infinity doesn't look very well good up there. Neither does my n. All right. The limit comparison test says this. If an bigger than 0, bn bigger than 0. All we're requiring here is everything has to be positive. Oscillating series don't work here. Alternating series don't work here. Right? They must both be positive terms. Now, what we're not saying is which one is larger than the other. So that's not a requirement for the limit comparison test. It's a little more generalized statement. Yes, they must be positive, but we don't care which one's bigger or smaller. All right? Then it says this. Suppose the limit as n goes to infinity. And which one do I want to put on top? It doesn't really matter. I want to put an over bn. So you take this expression in the numerator, this expression in the denominator, take the limit as n goes to infinity of that. And let's suppose that equals L. All right? Then, if L is finite and positive, which means it's neither infinity nor negative infinity. Well, it can't be negative infinity because we know it's positive here, valued here. So it is not infinity. And it must be positive. Well, we know it can't be negative, so you think, well, why would you bother? Well, remember, this is not 0. It is not 0. 0 is neither positive nor negative. So when I say that L must be positive, what I mean is it's got to be strictly greater than 0. All right? If it's finite and positive, then what we say is the series agree. We say they agree. Either they're both converge or both diverge. Either they both converge or they both diverge. Again, now the proof of this is straightforward. It actually is based upon the direct comparison test. If we went through a proof of this, the limit comparison test, in order to prove this statement is correct, you would use the direct comparison test as the theoretical tool to make that happen. I'm going to forgo that for now at least, and we'll accept this as correct. The text gives a really clear demonstration, a very clear argument as to why this is correct, and you can read that if you like. We're going to accept the limit comparison test. So what does this mean? Typically, as a matter of practice, usually the way this works is this. This is the series of interest. AN is the series whose behavior you want to learn. BN, this is the series with known. This is the one with known behavior. This behaves the way we know the way this behaves. This is the one we're investigating. This is the series we're investigating. This is the series whose behavior we know. And what we're saying is if you do the limit, if that's finite and positive, if it's finite and positive, then they either both converge or they both diverge. And we'll do several examples of each of these to get a feel for how each of these things work. All right? So let's see if we can make this happen here. We can illustrate what's going on with the limit comparison test. All right? So what I'm going to do is stop here, and we'll start with a new video with actual application of specific examples of the limit comparison test.